Hey, we are here. Oh my goodness. What is going on, everyone? Welcome to our second edition of the Vector Space Talks. Look at that. There's celebrations already happening because this is about to be a really cool event. We've got two speakers today, and the first one was a bit of a special guest announcement. We threw them in last minute because they had a big announcement over the past couple weeks. And so we've got Nils coming on, going to be talking about Cohere's embedding model. We've also got Filip coming on later to talk about music and AI and all kinds of fun stuff that he's done with Quadrant. So I cannot wait. Hopefully, you all cannot wait. Let us know, get active in the chat. That's probably the best part about watching this stuff live. Ask us questions. Let us know if things are resonating with you or not. And I'll be monitoring it so that you can ask any kind of question you may have. And I can jump in and ask Nils if it warrants a stop in his presentation, or we can ask him at the end and we can have a little bit of discussion. So I think the first talk is going to be about 10 minutes, 10, 15 minutes, and then we got 10 minutes planned for Q&A. Without further ado, I've got my man Nils around. Where's he at? There he is. Hey.
Great. Thank you for being here and also inviting me last minute. I have two technical topics today, I think, which will be really interesting for anyone in the embedding space, which also work really well with Qdrant as vector database. Happy to talk more on this and show
Dude,
people more on like embeddings and what's going on, what's the newest innovation in the space.
it's all about the embeddings, baby. So I'm going to kick it off to you. I will share your screen real fast and I'll get out of the way. And I look forward to hearing about this. It's super exciting news. So here we go, man.
Oh, great. As mentioned, we launched last week the version 3 of our embedding models. It was a really cool project. A lot of the team has been working on really get positive from beta testers so that we said make it public. On the one side, it's a state-of-the-art model in 100 languages on different well-known benchmarks like the massive text embedding benchmark or the information retrieval benchmark BEER. But here I want to talk a bit more on like two interesting critical model innovations. One is like content quality estimation, and the other is compression-aware training. So in embeddings, for a really, really long time, embeddings were mostly measuring the topic match. So you have a query and you have a document and you want to know how similar are these on the topic. But in information retrieval and search, you not only care about like, is it on the same topic, but which document is the most informative. So for example, let's say you have a collection of documents. COVID-19 has many symptoms. COVID-19 symptoms are bad. COVID-19 symptoms are not nice. And then you have two documents, paragraphs. COVID-19 is a disease caused by a virus. The most common symptoms are fever. COVID-19 symptoms can include. And then you have at the end one about dementia, that it has the following symptoms. And here you quickly notice, so if you have a collection like this and you run a query, a search query, hey, what are the COVID-19 symptoms? And you take a model, for example, from OpenAI or from sentence transformers, and just measures topic similarity. The top three results will be COVID-19 has many symptoms, COVID-19 symptoms are not nice, COVID-19 symptoms are bad. So obviously, if you show this on the left to a user and they say, yeah, that's interesting that COVID-19 has many symptoms and that they are not nice, but it's not really, really informative. And many people now use these embeddings also in these retrieval augmented generation, RAG, where you ask the RAG model, hey, write about this. And then the generate model can only say, okay, it has many symptoms and the symptoms are not nice. But it leaves like a really bad feeling to the user. In contrast, on the right, what do we see? A model that measures content quality also. It retrieves the most informative first. So it says, okay, this document is the most informative. It provides you detailed information about COVID-19 symptoms. This is also providing detailed information on COVID-19 symptoms. And the last one, it's on COVID-19, but has not really detailed information on it. And so it makes a really big difference if you work on larger quantities of data. So at Cohere, we're focusing heavily on these big use cases where you want to have search over like a lot of data. And then if you have a lot of data, you often have like content that's not really informative and content that's really informative. And here the model is able to differentiate what's informative and what's not informative. And how to do it. So big challenge is that previous models, many models and many training pipelines, they just measure topic. So they look at the query, they measure topic similarity, and then they just decide on a topic similarity. And if you look at these two documents, if your query is COVID-19 symptoms and document A is COVID-19 has many symptoms, document B is COVID-19 is a disease caused by a virus, the most common symptoms are, and then many more words on the symptoms, you see that the topic similarity of query and document A is higher than the topic similarity of query and B, because document B is not only on symptoms, it's also on that it's caused by a virus. So it's not that good on a topic similarity, but obviously we, as human, typically we like more informative answers. So we like the one which provides us background information, and also for RAG, it provides we like the more informative information, the more informative paragraphs and documents, and we want to have these. And so what we do in the new model is to measure topic match and content quality. So you can think about a simplification of it is you think about a certain set of dimensions, measure the topic match. So how similar is the query and the document on a topic? Are both talking about COVID-19 symptoms? And then a fraction of the dimensions talk about content quality. And what you could do, for example, in the setup, so you have a query encoder. So here it becomes critical that you have two different encoders. Query encoder that encodes your query as first dimension is 1, and then the other dimension you encode the topic. And then you have a document encoder that measures the quality of the document and the topic of the document. And then if you compute the dot product here in this case, you say, okay, the final result is like 1, so the one from the query times the dimensions on the quality from document plus the similarity of the query and the document on the topic. So it's measuring the quality and the topic. In reality, we let the model learn how to encode topic and content quality in the space. So we don't say, okay, dimension 1, 2, 3 are on content quality, but we let the model figure out itself how to train these. And as mentioned, it makes big difference on many scenarios. So Track COVID is a nice example data set on COVID-19 scientific papers from a web crawl, really noisy, many challenges what you have with web crawl, that data is incomplete and missing and not correctly extracted. So here we see a big boost. Another interesting data set is on Hotpot QA, which is a multi-op question answering data set from Wikipedia, where it's also helping a lot to find the documents that are most informative on your query to answer the query. So content quality is not just measuring the text length, but also how much information is on a topic. So you could say, okay, you could sort these just by text length, but here we added like some examples in it, like COVID-19 has many symptoms, and now I add some text without a lot of meaning just to see if the model only depends on context length or on quality. And here's also like something which is like really short on COVID-19 symptoms, but then I provide some information on my cat. So here we see, okay, the model says, okay, these two, I don't like them. It's still on COVID-19, so it's better than the document on dementia, but it's like worse than the short one and worse than the one that has a lot of information on topic. So it's a really cool feature. I think people really like it if you have these scenarios where you have like a lot of redundancy in your corpus and the content quality is like really different. It has limitations, factual correctness. It cannot reliably differentiate between true and fake statements. So it's not designed for that. It's in general a really hard problem to detect these fake statements and to solve it. It can do it to some degree when it's part of the pre-training data set. So if I ask like COVID-19 symptoms and I have to text COVID-19 symptoms, coughing and memory loss, the model knows, okay, it's COVID-19 is stronger connected to coughing, but it's not reliable. Also, temporal aspects are a challenge. So it cannot differentiate if a statement is still true. If you say, okay, there are no COVID-19 vaccines and there are several COVID-19 vaccines, the model, both can be true depending on the time when the statement was made, but the model is not able to resolve this. And obviously, it cannot solve the trustworthiness of a source. So is the information from the CDC, or does some random person on Twitter wrote this? So it's obviously not perfect. These aspects are also really, really critical. But we're going in the direction where we also want to tackle it. But so far, just on a text level, it's working very well. In terms of training, bit of like challenges in training. So common way to train these embedding models is constructive training, where you say, okay, you take a batch with queries and answers. Issue is here that you just have like one document in it that's on the topic and that's relevant. So here you have like 3 things, and then you say COVID-19 symptoms. Out of the 3 answers, which one is correct? But it doesn't differentiate between any rankings. So what we did is take queries. So we got like millions of queries and retrieve top K documents, all documents relevant on it, and then ask a large content quality model, what's the preference? So it's basically preference learning for embeddings. Out of these 3 documents, what's the preference? And then from the model, we know, okay, document 2 is preferred over document 1 is preferred over document 3. And then backprop this to the embedding model, and we say, okay, give us document 2 over document 1 over document 3. The other aspect, which we're going to announce soon, so here you get a short sneak, compression training. Why compression? So the challenge, if you have a billion float embeddings and you run Qdrant, you host it yourself on AWS, it becomes really, really expensive. So if you have like 1,500 dimensions, you need like 6 terabytes of memory per instance. You add some redundancy to it. You look at your EC2 instance price at the end, and it hits you with like $500,000. One way to reduce this is to go to like fewer dimensions. So if you use an embedding model with like 384, it goes from like $500,000 to like close to 200K per year. But still, 200K per year, that's quite expensive. And it's really preventing, because a billion embeddings, that's not so much. So many of our customers hitting in this range, in the billion range. Qdrant on Twitter, or on X, probably also. I mean, Twitter has like 500 million tweets, or used to have 500 million tweets a day. So every second day they have like 2 billion tweets per day. So it becomes like really, really expensive to run the vector database. So what we need to do is reduce the memory footprint. And here compression helps to reduce it 10 times, 100 times, 1,000 times. And then at the same time, your cost for EC2 reduces. One cool feature in Qdrant is these binary embeddings. It's 32 times smaller, 40 times faster. It's a simple binarization. If the float value is bigger than 0, set it the bit to 1, else set it to 0. And then you operate in this binary space. However, the question is, how well do embedding models support binarization? And the quality of the binarization depends on the model. So if you have a model which looks like this, produces embeddings, they are all up here. If you binarize it, all these 4 embeddings are squashed to the same binary embedding. And then the model performs really badly. So if you take an open source model, E5, nice model, if you work in a float, it runs at a comparable performance as our Cohere model. But if you do the binarization, you see, okay, you get like a 40% drop in search quality. While if the model is trained with compression aware, you just get like 8% search quality drop. And so this really enables to get these compressions in and say, okay, maybe for my application, 92%, that's good enough for my use case. But the 62% of search quality, that's maybe too bad. And what does compression aware training do? So instead of like squashing all these embeddings in these tiny subspace, the vector space becomes kind of like nice and nice for these binarizations. So in this case, we would blow it up, make sure that the embeddings are nicely sorted over these different sections. And then you can run compression nicely on it. The other aspect also in Cohere is these product quantization. Basically, what you do in product quantization, you take the dimensions, you put it into subgroups, and then in each subgroup, you create a cluster. So here we have 2 dimensions. For every dimension, you create 4 clusters. And then at the end, if you take the combination, you have 16 clusters. And the issue here is, again, for the vector space, we see some clusters here around here where a lot of black dots, a lot of embeddings are, and down here is only like a single one, so it's imbalanced. And this is like really, really hurting the cluster performance. And here again, we do compression aware training. So to make the model really aware of these compression techniques, so that not all the embeddings, that we don't have like high density here and a low density here, but in the best case, an equal density in all these cluster points. And this again makes a big difference. So if we run like 64x compression with an open source model E5, which was not trained for it, we see we lose like half of the search quality. So search quality becomes like really, really bad at this compression. And with compression aware training, you can keep most of the search quality. And yes, so this like two aspects we did, especially for these large scale deployments. Content quality, it's critical for any noisy data set. So as soon as you have a noisy data set, you will see a big difference. If you have a perfectly nice, clean data set without any redundant information, then content quality is not that critical. But as soon as you hit some scale, you have redundant information with different quality levels, and you want to serve as the most informative. Again, at scale, compression-aware training is critical. It allows you to lower your memory footprint of Cohere, which reduces the cost on AWS, on your cloud provider. So that's nice if you can search on more data and pay less and still have a good quality. You can use the model Ether via our API. So you pay per byte token of 0.001 cent or dollar per 1,000 tokens. Deployed on SageMaker. So we're big on like private deployments where we bring it to your cluster, or you check it out on SageMaker or AWS Bedrock, where you get it in your VPC, highly optimized, so 5 millisecond latency. And then you get like a really good performant embedding model and combine it with a great vector database like Cohere. That's so much from my side.
Dude, very good stuff. I really like this, and I have so many questions. I saw there's some questions coming through in the chat too. So while people are asking their questions in the chat, I have to ask you, can you talk to me more about this content quality model? What is that?
Yeah, sure. So basically, it's a bit inspired from this reinforcement learning from human feedback. So in generative models, it's a trick we're using for quite a long time for any generative model, where we say, okay, this is prompt, write me about COVID-19 symptoms. And then the model generates either response 1, COVID-19 has many symptoms, or response 2, COVID-19 is a disease caused by a virus. And then in this reinforcement learning from human feedback, we ask humans, hey, this was your task. Which of these 2 documents is more informative? and then you learn a model on it. So that the model learns, okay, this is a preference. If this is a question, that's the response. And we took this model and brought it back to these embedding training that we say, okay, here we have these preference data. If you search for this information, what do humans prefer? The model can estimate it, and then we throw it at the model. So we take like millions of queries, show them several documents, say, okay, here's a document A on this, here's a document B on this. The content quality says, okay, I think document A is better than document B. And then we check in the vector space, is the similarity of query of document 2 better than or higher than the similarity of query and document 1. So it's basically taking these preference learning back to embeddings.
I love it, man. Yeah, it's so good and it's so interesting to think about. I mean, the uh the use for that and the benefits that you can have from that. So, hats off to you. Now I'm going to start asking some questions from the chat. We've got one coming through that's asking from Andre V. Is it possible to evaluate quality of the embeddings, garbage or meaningful, just by looking at the vector itself without the relative comparison?
No. So it's a mistake people often do. They look at the embeddings. Sometimes they look at the cosine similarity scores. Is it like
Yeah.
60? Like in this case, here we get like a similarity of like 0.72 and then try to estimate on this. But embeddings, it's always about these relatives. I mean, I could just multiply the score by 2 or divide it by 2 or do whatever, add 0.1 to it. It's always about these relatives. Like, is this more similar than this? And is the ranking we get here doesn't make sense at the end?
Yeah. Okay. Good to know. So Renee's asking one in the chat, and this is a little bit LangChain specific. He's saying, as far as I know, the new embeddings need a parameter input type. So far, that is not supported by langchain.embeddings.cohere.cohere embeddings. Will that be
Yeah.
fixed? And
Yeah.
when? Or is there a hack that we can do, some kind of workaround?
Yeah. We're working on it to get it into LangChain. The input type is critical because we need these differentiations. So it's critical that the model know, is it the query or is it the document? So that it can say, if it's a query, I search for content quality for documents with the highest content quality. So we're basically disabling these dimensions if it's a query. We set them to 1, so that it's just defined by the quality of the document. Because obviously it doesn't make sense to judge a user, hey, did you write a good query or a bad query? But it makes sense to judge it on the document. And yeah, we're working on it into these partners like LangChain, that you soon can use it. Workaround for now is just use the embeddings directly without LangChain. But hopefully soon it's also in LangChain.
Awesome. Excellent, man. Well, Niels, dude, it has been an absolute pleasure. I appreciate you coming on here as always. This is incredible to hear about what you all are doing and how you're doing it. I also really appreciate that you pulled back the curtain a little bit. You got to show us how you've been creating the special sauce. And so hopefully everybody can get out there and start using this embeddings and yeah, stress test them, try and break things, do whatever they can, and dude, and I hope to see you around Frankfurt sometime. I'm still trying to get you to come and present at the local meetup, so we'll talk
Yeah,
offline about that one, huh?
sounds great. Great for having me here, and looking forward to the second talk today.
Excellent, dude. Well, yeah, speaking of the second talk, I'm gonna bring Philip on. Where you at, Philip? There he
Hi,
is.
hello.
Hey, dude. How'd you like that talk from Nils
Uh,
while he's
it,
on
it,
here? Be
yeah.
careful what you say.
It was amazing. I mean, it's really nice to see kind of the work going on with time, especially you'll see with my project, like I'm kind of referencing stuff from Neil's previous work.
Nice.
So I think it fits in quite well together.
Excellent.
Yeah.
Yes. And so, for those who do not know, you are going to be talking to us about when the music we listen to does not match our vibe. And can we get AI to help us on that? And you're currently working as a data scientist at Marks and Spencer. I know you got
Yeah.
some slides to share, right? So
Yeah.
I'll let you share your screen. We can kick off the slides, and then we'll have a little presentation, and I'll be back on to answer some questions. And if Niels is still around at the end, which I don't think he will be able to hang around, but we'll see, we can pull him back on and have a little discussion at the end of the chat. So,
That's great.
all right,
Okay,
cool.
cool. I'll share my screen.
Right on.
Yeah.
There we
So
go.
yeah. So I had to use this slide because it was really well done as an introductory slide.
Nice.
Um,
Thank
so
you.
yeah, thank you also for making it. So yeah, the idea was and kind of the inspiration um, with music. We all listen to it. It's part of our lives in many ways. Sometimes it's like the gym, we're ready to go. We're all hyped up, ready to do a workout, and then we click play. But the music and the playlist we get, it's just not what exactly we're looking for at that point. Or if we like try to work for a few hours and try to get concentrated and try to like code for hours, we can do the same and then we click play, but it's not what we're looking for again. So my inspiration was here, like, was it possible to somehow maybe find a way to transfer this feeling that we have, this vibe, and get the help of AI to understand what exactly we need at that moment in terms of songs. So the obvious first question is, how do we even capture a vibe and feel of a song? So initially, one approach that's popular and that works quite well is basically using a data set that has a lot of features. So Spotify has one data set like this, and there are many others, open source ones, which include different features like loudness, key, tempo, different kind of details related to the acoustics, the melody, and so on. And this would work, and this is kind of a way that a lot of song recommendation systems are built. However, what I wanted to do was maybe try a different approach, in a way, try to have a more unconventional recommender system, let's say. So, what I did here was I tried to concentrate just on language. So my idea was, okay, is it possible to use human language to transfer this experience, this feeling that we have, and just use that and try to maybe encapsulate these features of songs, and instead of having a data set, just have descriptions of songs or sentences that explain different aspects of a song. So, as I said, this is a bit of a less traditional approach, and it's more of kind of testing the waters. But it worked to a decent extent. So what I did was, first I created a data set where I queried a large language model. So I tried with Llama and ChatGPT both, and the idea was to ask targeted questions. For example, like, what movie character does this song make you feel like, or uh, what's the tempo like? So different questions that would help us understand maybe in what situation we would listen to this song, how will it make us feel like, and so on. And the idea was, as I said again, to only use song names as queries for this large language model. So not have the full data sets with multiple features, but just song name, and kind of use this pre-trained ability of all these LLMs to get this info that I was looking for. So an example of the generated data was this. So this song called Deep Sea Creature, and we have like a small description of the song. So it says a heavy, dark, mysterious vibe. It will make you feel like you're descending into the unknown and so on. So a bit of a darker choice here, but that's the general idea. So trying to maybe do a bit of prompt engineering in a way to get the right features of a song, but through human language. So that was the first step. So the next step was how to encode this text. So all of this kind of querying reminds me of sentences, and this led me to sentence transformers and sentence BERT. And the usual issue with kind of doing this sentence similarity in the past was this, what I have highlighted here. So this is actually a quote from a paper that Nils published a few years ago. So basically the way that this similarity was done was using cross encoders in the past, and that worked well, but it was really slow and unscalable. So Niels and his colleague created this kind of model which helped scale this and make this a lot quicker, but also keep a lot of the accuracy. So Bert and Roberta were used, but they were not, as I said, quite scalable or useful for larger applications. So that's how sentence BERT was created. So the idea here was that they would be like a Siamese network that would train the model so that there could be like two BERT models, and then the training would be done using this like 0, 1, and 2 tags, where kind of the sentences would be compared, whether there is entailment, neutrality, or contradiction. So how similar these sentences are to each other. And by training a model like this and doing mean pooling in the end, the model performed quite well and was able to kind of encapsulate this language intricacies of sentences. So I decided to use and try out sentence transformers for my use case. And that was the encoding bit. So we have the model, we encode the text, then we have the embedding. So now the question is, how do we actually generate the recommendations? How is the similarity performed? So the similarity was done using vector spaces and cosine similarity search. Here there were multiple ways of doing this. First, I tried things with a flat index, and I tried quadrant and I tried FICE, so I've worked with both. And with the flat index, it was good. It works well. It's quick for small number of examples, small number of songs, but there's an issue when scaling. So once the vector indices get bigger, there might be a problem. So one popular kind of index architecture is this one here on the left. So hierarchical navigable small world graphs. So the idea here is that you wouldn't have to kind of go through all of the examples, but search through the examples in different layers, so that the search for similarities quicker, and this is a really popular approach. And Quadrant have done like a really good customizable version of this, which is quite useful, I think, for very larger scales of application. And this graph here illustrates kind of well what the idea is. So there is the sentence. In this example is like a striped striped blue shirt made from cotton, and then there is the network or the encoder. So in my case, this sentence is the song description. The neural network is the sentence transformer in my case. And then these embeddings are generated, which are then mapped into this vector space. And then this vector space is queried, and the cosine similarity is found. And the recommendations are generated in this way so that once the user writes a query, and the query mentions like some kind of a mood, for example, I feel happy and it's a sunny day and so on, you would get the similarity to the song that has this kind of language explanations and language intricacies in its description. And there are a lot of ways of doing this, as Nils mentioned, especially with different embedding models and doing context related search. So this is an interesting area for improvement even in my use case. And the quick screenshot looks like this. So for example, the mood that the user wrote, it's a bit rainy, but I feel like I need a long walk in London. And these are the top 5 suggested songs. This is also available on Streamlit. In the end, I'll share links of everything. And also after that, you can click create a Spotify playlist, and this playlist will be saved in your Spotify account. As you can see here, it says playlist generated earlier today. So yeah, I tried this, it worked. I will try live demo a bit later. Hopefully it works again. But this is in beta currently, so you won't be able to try it at home because Spotify needs to approve my app first and go through that process so that then I can do this part fully. And the front end bit, as I mentioned, was done in Streamlit. So why Streamlit? I like the caching bit. So of course, this general part where it's really easy and quick to do a lot of data dashboarding and data applications to test out models, that's quite nice. But this caching options that they have help a lot with like loading models from Hugging Face, or if you're loading models from somewhere, or if you're loading different databases. So if you're combining models and data, in my case, I had a binary file of the index and also the model. So it was quite useful and quick to do these things and to be able to try things out quickly. So this is kind of the step-by-step outline of everything I've mentioned and the whole project. So the first step is encoding these descriptions into embeddings. Then this vector embeddings are mapped into a vector space. Examples here with how I've used Quadrant for this, which was quite nice. I feel like the developer experience is really good, and for scalable purposes, it's really useful. So if the number of songs keep increasing, it's quite good. And the query and more similar embeddings, the front end is done with Streamlit and the Spotify API to save the playlists on the Spotify account. All of these steps can be improved and tweaked in certain ways, and I will talk a bit about that too. So a lot more to be done. So now there are 2,000 songs, but as I've mentioned in this vector space, the more songs that are there, the more representative this recommendations would be. So this is something I'm currently exploring and doing. Generating filtering and user specific personalization. So once maybe you log in with Spotify, you could get recommendations related to your taste on Spotify or on whatever app you listen your music on. And referring to the talk that Niels had, a lot of potential for better models and embeddings and embedding models. So also the contrastive learning bits or the content aware querying that could be useful too. And a vector database, because currently I'm using a binary file, but I've explored Quadrant. And as I said, with Spotify Web API, there are a lot of things to be done with this specific user created recommendations. So with Quadrant, the Python client is quite good. The getting started helps a lot. So I wrote a bit of code. I think for production use cases it's really great. So for my use case here, as you can see on the right, I just read the text from a column and then I encode with the model. So the sentence transformer is the model that I encode with. And there is this collections that they're so-called in Quadrant that are kind of like this vector spaces that you can create. And you can also do different things with them, which I think one of the more helpful ones is the payload one and the batch one. So kind of you can batch things in terms of how many vectors will go to the server per single request. And also the payload helps if you want to add extra context. So maybe I want to filter by genres, I can add useful information to the vector embedding. So this is quite a cool feature that I'm planning on using. And another potential way of doing this and kind of combining things is using audio waves to lyrics and descriptions and combining all of this as embeddings and then going through the similar process. So that's something that I'm looking to do also. And yeah, you also might have noticed that I'm a data scientist at Marks and Spencer. And I just wanted to say that there are a lot of interesting ML and data related stuff going on there. So a lot of teams that work on very interesting use cases, like in recommender systems, personalization of offers, different stuff about forecasting. There is a lot going on with causal ML. And yeah, it's the digital and tech department is quite well developed, and I think it's a fun place to explore if you're interested in like retail data science use cases. So yeah, thank you for your attention. I'll try the demo. So this is the QR code with the repo and all the useful links. You can contact me on LinkedIn. This is the screenshot of the repo, and you have the link in the QR code. The name of the repo is Song Vibe. A friend of mine said that that wasn't a great name of a repo. Maybe he was right, but yeah, here we are. I'll just try to do the demo quickly, and then we can step back to the discussion.
Yes.
Yeah.
I love, dude, I gotta say, when you said you can just automatically create the Spotify playlist, that made me go like, oh, yes, I
Yeah,
want that.
Let's see it if it works locally. Do you have any suggestion? What mood are you in?
Oh, I was hoping you would ask me, man. I am in a bit of an esoteric mood, and I want female, kind of like Gaelic voices, but not Gaelic music, just Gaelic voices and lots of harmonies, heavy harmonies also. You didn't
Let's see if that
you didn't
if this
realize you were
works.
asking a musician, huh? Let's see what we
Yeah.
got.
Let's see if this works in 2000 songs. Okay, so these are the results.
Okay.
Um, yeah, I'd have to
Listen to
send
him.
you the playlist. Let's see.
Yeah. Can you make the playlist public? And then I'll just
I
go
can.
find it right now.
I
There we
think
go.
so. Let's see. Okay, yeah. Open in Spotify.
I'll
So
give
it
you.
should. Yeah, there's
Oh,
the Spotify
nice.
playlist created. Yeah, now. Okay, cool. I can also rename it. What
Yes.
do you want to name the playlist?
Esoteric Gaelic harmonies. That's what I think we got to go with.
Yeah,
AI
deal.
well, I mean,
Yeah.
maybe. We could just put maybe in parentheses.
Yeah, yeah. So
Nice.
I'll share this later with you.
Excellent.
Um, but yeah, basically that was it.
It worked. I
Yeah,
mean, 10 out of
yeah,
10 for it working. That is also very
yeah.
cool.
Live demo working. That's good. So
That's
now
a
doing
plus.
the infinite screen, yeah, which I have stopped now. Yeah,
Classic. Dude, well, I've got some questions coming through and
yeah,
the chat's been active too. So I'll ask a few of the questions in the chat for a minute, but before I ask those questions in the chat, one thing that I was thinking about when you were talking about like the next step is getting better embeddings. And so was there a reason that you just went with the song title and because it kind of and then did you check? You said there was 2000 songs or how many
yeah,
songs?
yeah,
So did you do anything to check the output of the descriptions of these songs?
yeah. So I didn't do like a systematic testing in terms of like, oh yeah, the output is structured in this way.
Uh-huh.
But yeah, I checked it like roughly, mm, went through a few songs and they seemed like, I mean, of course you could add more info, but they seemed okay. So I was like, okay, let me try kind of whether this works. And yeah, the
Yeah.
descriptions were nice. Yeah,
Awesome. Yeah, so that kind of goes into one of the questions that Morney's asking.
yeah,
Are you going to add, let me see, are you going to team this up with other methods like collaborative filtering, content embeddings, and stuff like that?
yeah, yeah. I was thinking about this different kind of styles, but I feel like I want to first try different things related to embeddings and language, just because I feel like with the other things, with the other ways of doing these recommendations, um, other companies and other solutions have done a really great job there. So it's not, I wanted to try something different to see whether that could work as well or maybe to a similar degree. So that's why I went towards this like approach rather than collaborative filtering or yeah.
Yeah. Yeah, yeah. It kind of felt like you wanted to test the boundaries
Yeah.
and see if something like this, which seems a little far-fetched, is actually possible. And it seems
Yeah.
like I would give it a yes.
Yeah,
And
it wasn't that far fetched actually once you
yeah.
see it working. Yeah.
Yeah, totally. One thing that another question is coming through is asking, is it possible to merge the current mood, so the vibe that you're looking for, with your musical preferences?
Yeah, so I was thinking of that when, so like when we're doing this, the playlist creation that I did for you, there is a way to get like your top 10 songs or your other playlists and so on from Spotify. So my idea of kind of capturing this added element was through Spotify like that. But of course, it could be that you could enter that in your own profile in the app or so on. So one idea would be how would you capture that preferences of the user once you have the user there. So you need some data of the preferences of the user.
Yeah.
So that's the problem. But of course, it is possible.
You know what I'd love is, like in your example, you put that I feel like going for a walk, or it's raining, but I still feel like going through for a long walk in London, right? You could probably just get that information from me, like what is the weather around me, where am I located, all that kind of stuff. So I don't have to give you that context. You just add those kind of
Yeah,
contextual things, especially weather. And I
yeah,
I get the feeling that that would be another unlock too. Unless you're like you are the exact opposite of a sunny day on a sunny day, and it's like, why does it keep playing this happy music? I told it I was sad.
yeah. Yeah,
Uh,
you're predicting not just the songs, but the mood also. So
yeah, yeah,
you
totally.
don't have to type anything, just open the website and you get
Yeah,
everything.
exactly. Yeah, give me a few predictions just right off the bat, and then maybe later we can figure it out. The other thing that I was thinking could be a nice add-on. I mean, the infinite feature requests. I don't think you realized you were going to get so many feature requests from me, but
No.
let it be known that if you come on here and I like your app, you'll probably get some feature requests from me. So I was thinking about how it would be great if I could just talk to it instead of typing it in, right? And I could just explain my mood or explain my feeling and even top that off with a few melodies that are going on in my head, or uh, a few singers or songwriters or songs that, I really want something like this, but not this song. And
Yeah,
then also add that kind of thing
you
too.
do the humming sound a bit and you play your melody, and then you get.
Except I hum out of tune, so I don't think that would work very well. I'd get a lot of random songs, that's for sure. It would probably be just about as accurate as your recommendation engine is right now. So, yeah, well, this is awesome,
Yeah,
man. I really appreciate you coming on here. I'm just gonna make sure that there's no other questions that came through the chat. Nope, looks like we're good. And for
thank
everyone
you.
out there that is listening, if you want to come on and talk about anything cool that you have built with Quadrant, or how you're using Quadrant, or different ways that you would like Quadrant to be better, or things that you enjoy, whatever it may be, we'd love to have you on here. And I think that is it. We're going to call it a day for the Vector Space Talks #2. We'll see you all later. Philip, thanks so
Yeah,
much for coming on
thank
here,
you.
man.
My
I
my
really appreciate
pleasure.
it. Now
Thank
I'm
you.
gonna I'm gonna end it off with some music, just in memory of your presentation. So I'll see y'all
Thank you.
later.